And hello everybody, here are your notes for graphing secant and cosecant trig functions. To understand the graphs of secant and cosecant, we need to understand that they are the reciprocals of cosine and sine, and then we also need to kind of understand what happens to a number when we take the reciprocal of it. So for example, let's say we had some fractions. So let's say these are our y values coming off of a sine or cosine function. So if we had a y value of, let's say, a half, let's say our sine or cosine ratio was a half, then what would the secant or cosecant ratio be? We would take the reciprocal of that, and when we do, it's going to become 2. So notice this fraction, when we reciprocate it, it becomes a larger number, something bigger than 1. In this case, it's going to be 2, or 2 over 1. If you had a third, and you reciprocate that, you're going to get 3. If you had a fourth, and you reciprocate that, you're going to get 4. So if you flip a fraction, the smaller the fraction is, the bigger the number is when you reciprocate it. If you had, for example, a 1, when we reciprocate that, we're going to get 1. And then one of the tricky ones, let's say you had a sine or cosine ratio of 0, so 0 to 1. When you flip this, you're going to get 1 over 0, which in this case is going to be undefined. So this idea is going to kind of show up when we're making the graph. If we have fractions, when we flip them, they're going to become larger numbers. If we have 1, when we flip a 1, we're going to stay with a 1. And if we have to reciprocate the number 0, when we reciprocate 0, you basically get something that does not exist, so undefined. So this is going to kind of come into play when we're trying to make our cosecant and secant graphs. So let's go ahead and take a look at a few examples. And here's our first example. So they want us to just do a graph of secant. So to graph secant, you first have to graph its reciprocal. So the reciprocal of secant should be cosine. So what you want to first be thinking is just, what does the graph of cosine look like? And we'll get a graph of cosine first, and then we'll plot out where all the reciprocal values are. So let's do a standard parent cycle or fundamental cycle of cosine. And we'll have 8 boxes be 2 pi. So that's going to be our 2 pi. And let's go 2 boxes, we'll have that be a unit of 1, so a ratio of 1. And this will be our output on the cosine wave, or a ratio of negative 1. And we know cosine starts high, and then goes to here, and then 4 boxes, we're at negative 1. 3/4 of the way through the cycle, we're back to 0. All the way through the cycle, we're back to 1 where we started. And that's going to be our cosine curve. So the reciprocal of 1 is going to get you 1. If we look at, let's say, another key point, right here we have a y value of 0. So the reciprocal of 0 should be undefined. So the graph is not going to exist right here. So you want to put in a vertical line showing that the graph is not going to exist there. The next one, when the y value is negative 1, the reciprocal of negative 1 should be negative 1. The 0, the reciprocal of 0 is going to be undefined. So we'll put in a asymptote here. And then the last one, the reciprocal of 1 again, is 1. So that kind of gets us three key points, plus the asymptotes where it's going to be undefined. So the asymptotes is a portion of the graph that does not exist, so the function is undefined there. And then the next question is, what happens to all the other y values? So all these y values that are less than 1, we said at the beginning of the lesson that if you take a fraction and you take the reciprocal of it, it's going to get bigger. So for example, if you took a fraction of a half, it's going to become 2. If you have a third, it's going to become 4. So what's going to happen is all these fractions on the cosine curve are going to be reciprocated and become larger and approach that asymptote but never actually reach it. And then all these negative fractions are going to become larger negative numbers. And then all these fractions are going to become larger and approach your asymptotes. So the red is actually the final graph of secant. So we used the cosine wave to get us started. You don't need to erase it, but just the secant graph is technically just all the stuff in red. So your cosine graph was just there to kind of help us get started. That's not coming out as well as I thought it would. So again, you don't have to erase this. So there's our asymptotes and our curves. All right, we won't do that again. That didn't come out very good. So secant is just what you see in red. You have two asymptotes, and then you have the reciprocal curves making up the other part of the graph. And let's go do an example of cosecant. So making a graph of cosecant, we know that's the reciprocal with sine. So we want to start out with y equals sine. And then we will reciprocate all the y values. So let's do a graph of sine. And that's going to be 2 pi. And we'll have two boxes be a value of 1 on the vertical scale. So there's our sine wave. And then we want to put on the asymptotes. Where is its reciprocal going to be undefined? So wherever sine has a ratio of 0, a y value of 0, if you take the reciprocal of 0, it should be undefined. So it's going to happen right here. So you want to put in a dotted line there. It's going to happen here. And it's also going to happen here. And then the blue curve, all these fractions that are less than 1 are going to be larger than 1, and they're going to curve towards the asymptotes. And then these are going to be fractions being reciprocated. Negative fractions are going to become larger negative numbers in the negative direction. So that should be our graph. And in the book problems, you're probably going to be asked a few basic questions. So the first question you might be asked is, what's the period? Since cosecant and secant are just the reciprocal of sine or cosine, the period is going to be the same. So it still takes 2 pi to go through one complete cycle. So your period is going to be 2 pi. Unless you have some sort of period change. If you have a b value or some sort of transformation, then the period will change. But for the fundamental cycle, it should be 2 pi. The equation of the asymptotes, there's technically an infinite number of asymptotes. So notice if we look at these asymptotes, the first one is at x equals 0. The next asymptote occurred at pi, so x was equal to pi. So this one was at x equals pi. The next one was x equals 2 pi. So if we keep the pattern going, they're basically reoccurring every value of pi. So the next one would be 4 more boxes. And that's going to be at 3 pi. And if we kept going, the next one's going to be at 4 pi. And then those are going to go on forever in both directions. You could go in the negative direction. So we'd have an asymptote at x equals negative pi. And the pattern of your reciprocal curves is going to keep going. So this one is going up, the first one's going up, then it's going down, the next one would be going up, and the next one would be going down, and then this one would be, this one's up, so this one would be down. So this function continues on forever, just like the sine and cosine waves do. The asymptotes, we want to describe the asymptotes as far as what the x values are going to be. So notice the first asymptote, they usually start with the first positive or the 1 on the y-axis. So the first asymptote is at x equals 0. And then you want to describe how do you get to each asymptote after that. So similar to when we were talking about coterminal angles, we said they were going to be multiples of 2 pi. So if you remember coterminal angles, so coterminal angles, we would often say they're multiples of 360 or multiples of 2 pi if you're in radians. So similar concept here. How would I describe getting from one asymptote to the next? So if we were at x equals 0, how do we get to the next asymptote? You would have to add pi. And then the next one, how do you get to the next one? You would have to add pi. And then the next one, you would have to add pi. So what we can say is we can start at the first asymptote, x equals 0, and to keep getting to the next asymptote, we are going to add pi. So plus multiples of pi. So plus k pi. And then after that, you would probably simplify the 0 in this case. So x equals 0 plus k pi would just be x equals k pi. So your asymptotes are going to occur at some multiple of pi. So that would answer the asymptotes. And then the range is all your y values. So if we look at the range, it looks like your y values are going to go from 1 to infinity. So 1 to infinity, united or union with the set of numbers from, it looks like, negative 1 to negative infinity. And that's going to be your range. So 1 to infinity and negative 1 to negative infinity. And that's getting a little messy. Let's just clean these answers up on the next page. So they wanted to know what the period was. So the period was 2 pi. The equation for the asymptotes we said was going to be, so let's go equation of the asymptotes was going to be x equals k pi, and the range And they usually put it in order. So the range would go from negative infinity until you get to the y value of negative 1. And you are going to have a squared off bracket on this. It says we can actually use the y value negative 1. So the parenthesis means it's exclusive. The squared off bracket means it's inclusive. You can include negative 1 in the range value. United with, and then there's no values between negative 1 and 1, but when you finally get to the y value of 1, you're going to be on the graph again to infinity. So squared off bracket on the 1, because we can actually use the number 1, that's inclusive. Parentheses on the infinity, because we can't actually include the number infinity since we will never reach that number. So the squared off bracket is inclusive and the parentheses are exclusive.